In our previous lecture, we introduced LTI capacitor, our first dynamic component that we will study in detail, and later on it will be followed by the other dynamic component that we will study in detail, which is LTI inductor. Regarding the capacitor, what we did was we started with the definition of that component, and from that definition immediately followed the terminal equations, okay, where we saw that the current passing through an LTI capacitor is proportional to the rate of change of voltage appearing across its terminals, okay, and the ratio we called, which was a constant, we called the capacitance of the capacitor. Also, we saw that LTI capacitor, or capacitors in general, are able to store energy, okay, and we obtained the expression for the stored energy for our component LTI capacitor. Today, we will study some further properties of this dynamic device. So let's now talk about so-called initial condition models. For an LTI capacitor. Suppose that this capacitor is part of some circuit that we want to analyze. Okay. This is the voltage, this is its current, and here C, the constant, is its capacitance. Now, capacitor, as we said, is able to store charge, and the stored charge plays an important role, or affects the evolution of all the currents and voltages in the circuit that this capacitor is part of. Okay, therefore it must be at all times be part of the analysis. We cannot ignore it. And the initial charge produces this initial voltage across the terminals of the capacitor. Remember that charge Q equal C capacitance times the voltage appearing across the terminals of the capacitor. Okay. So this means that Q T0 minus is C times V0. Now this notation T0 minus means that, first of all, T0 is our initial time, okay, and T0 minus is a time that's arbitrarily earlier than T0, okay, so you can take this as T0 minus epsilon, where epsilon is a positive and an arbitrarily small constant. Okay. Now this is the initial charge of the capacitor. Okay. Now, for analysis, okay, it's usually desirable to work with a capacitor without initial voltage or without initial charge. Okay, that is, the initial charge equals an empty capacitor. So, but we cannot just ignore the initial charge of the capacitor and do our analysis, because this initial charge will make a difference in the evolution of the circuit that this guy is part of. Okay, so therefore, one way to go is instead of considering this device as a capacitor with some charge on it, we can always, well, there are two ways that we can represent this capacitor, a charged capacitor, with an empty capacitor with the same capacitance and some other component, some other device. Okay, and depending on that component, we have a different model, but all those models are equivalent. And what we mean by equivalent, I will define just soon. So let's call this the model 1, okay, capacitor with some non-zero charge, okay, initial charge. Now, for t greater than the initial time, which is t0 for all future times. This can be represented by, okay, this empty capacitor, a capacitor with no initial charge. Okay. But we also have to introduce some new device that will represent somehow the initial charge. And one way to do is represent that initial charge by an independent voltage source. Okay. And now here we have a two-terminal component, a capacitor, and now we also have a one-port. Okay, and this one-port, this two-terminal device, if you will, is equivalent to this charged capacitor if you choose carefully the voltage of this voltage source. Okay, first of all, we have to be careful about the labeling. Okay, this voltage here is now this voltage here, because now the terminals are this and that, and the current is here, the passing through capacitor. Now that since the capacitor and the voltage source are in series, so it's the same current that visits both. So this voltage, let's call it VC, and QT0 minus for this capacitor is now in this model is 0, and the capacitance of this capacitor is same as the capacitance of the original capacitor in model 1. Okay. And now, how about this voltage source? The voltage source produces voltage in a stepwise fashion. Okay, that's equal to the initial voltage of the capacitor. Okay, so therefore, this we call model 2. And we claim, and we're going to prove our claim, we claim that this device, or this model and that model, they are equivalent for all future times. And by future times we mean times t that are larger than the initial time t0. Now there's another way, it turns out, that the initial charge can be represented in a model which contains an empty capacitor, and it's the following. This is equivalent to so-called model 3. Plus minus V. This is I, the current. Here we have our empty capacitor with the same capacitance, C, empty, therefore Q T0 minus equals 0. So initially it's uncharged. And then to represent the initial voltage or initial charge of the capacitor in model 1, we use current source, and that current source is, the result is an impulsive current source, and the magnitude after integration is C V0. Okay, so it's impulsive, therefore it's C V0 times. C V0 delta T minus T0. Okay, and this delta is our unit impulse function. Okay. So now this is our model 3, and our claim is that these three models are equivalent to one another for future time, for T larger than T0. For that statement to be precise, let's be precise about what we mean by equivalent or equivalence. Okay. So by equivalence, which we denote by this 3-bar notation, we mean following. All three models will generate the same current and voltage IV characteristics for all times t larger than t0. So that's what we mean by equivalence, quite a simple definition. All three models will have the same VT, IT readings. Assume that they're connected to the same circuit. Readings for all future times. Okay. And the advantageous properties of the second and third model sometimes in analysis is that they contain an uncharged capacitor, whereas in model 1, in the original configuration, this capacitor is charged. Note that in the latter two models, models 2 and 3 capacitors are initially uncharged. Okay, or more informally, they are empty. Okay. Now let's prove this claim that these three models are equivalent, and where equivalence, definition of equivalence, is provided on the right. Okay, so the proof is really straightforward. All we're going to do is we're going to obtain the relation between the current and voltage for t larger than t0. If we obtain the same relation between current and voltage, so that means they enjoy the same IV characteristics, okay, for all future times t larger than t0, and that would prove our claim. Okay, proof goes as follows. Let's obtain the IV characteristics for model 1. Well, there's nothing to obtain because it's the capacitor that we studied in the previous lecture. All we have to do is just write the terminal equation directly. Let's write it in its integral form. Okay, so model 1 is producing the following IV relation: V T0 minus plus 1 over C initial time to after future time, and then what we integrate is we integrate the current passing through the capacitor, okay, d tau. And this is denoted by the constant or the number capital V0. Okay, so let's replace that. Plus 1 over C I tau d tau. Okay. Now, if those three models are equivalent, it would mean that for model 2 and model 3, we should have the same voltage current relationship. And let's see that it's actually the case. Let's move on to model 2. Okay. V of t this time equals, okay, this is for t larger than t0. We have V t0, okay, the notation was Vc, right? No, V. Vt equals V t0 minus plus Vc. So this voltage in model 2 equals the voltage of the capacitor, which is empty, plus the voltage of the independent voltage source. Now, The capacitor's voltage is again by terminal equation. Vc T0 minus plus 1 over C T0 minus 2T I tau d tau. Okay. So this is the capacitor in the second model, and by assumption that capacitor is empty. It's chargeless initially, and that means the initial voltage is 0. Vc T0 is 0. Okay. Plus, because this voltage is not the voltage of the capacitor only, it's voltage of the capacitor and the voltage of the independent voltage source. Therefore, to this term, the capacitor voltage VCT, we also have to add the voltage of the independent voltage source, which is V0 ut minus T0. Okay, so this is 0, goes by assumption, because we're working with an empty capacitor. And this thing is for t larger than T0, that is when, for all t's that make the argument of this step positive, this is 1. Okay, so we have 1 times V0. We have that equals V0. So this is equal V0 for t larger than T0. Okay. And then rearranging the terms, here we have V0 plus 1 over C T0 minus Ti tau d tau. Okay, the same as the first term in the equation. Of course, to be able to write this, we have to be dealing with times larger than T0. Okay. So for t larger than T0, we have to put somewhere near the equation. Okay, so what we have proved is that at least model 1 and model 2, they're equivalent for t larger than T0. Now let's also see what model 3 tells us. Okay. So model 3, V of t, this voltage equals the voltage of the capacitor. Okay. The voltage of the capacitor is the initial capacitor voltage, which is 0 because the initial capacitor charge is 0, plus 1 over C, 1 over capacitance, and then we're going to integrate the current passing through the capacitor. Note that the current passing through the capacitor is not this current only, but there's also the current coming from the current source. Okay, the current coming from the current source is this, and then we have I coming from the outer terminal. And then the sum must be the current that's flowing through the capacitor. So therefore we have, as for the capacitor current in this configuration, is I tau plus this current, which is CB0 delta tau minus T0 and d tau. Okay, first of all, this thing is 0 by assumption because this capacitor is empty. And then now let's work out what that integration gives us. So that equals, let's separate the integrand and write that integral as 2 separate integrals. Okay? So what we have is V0. Okay? We can take this CV0 out. This C will cancel with this 1 over C, and we will be left with V0 multiplying the integral delta tau minus T0 d tau plus we have the integral of the current 1 over C T0 minus Ti tau d tau. Okay. Note that by definition of impulse function, this integral gives us 0 for t smaller than T0 and 1 for t greater than T0. Okay, so since we're interested in what happens at future times for t larger than T0, this integral gives us 1. Therefore, multiplied by V0, this whole term will be V0 for t larger than T0. Okay, so this equals 1 for t larger than T0. Therefore, this equals V0 plus 1 over C T0 to Ti tau d tau for t larger than T0. Therefore, for all three models, model 1, model 2, and model 3, we have the same voltage current relationship, and we can therefore claim that those three models are equal. Now we'll talk more about equivalence in different cases. Okay. For instance, let's consider a number of LTI capacitors in parallel connection. Okay. Remember, for LTI resistors, if we had some number of them in parallel connection, and that connection, when we consider that connection as a single one port, that one port can be represented by a single LTI resistor whose resistance is called the equivalent resistance, input resistance, or sometimes effective resistance of that one port. Now we're going to investigate whether something similar can be done with the capacitors, and it turns out that it can. Okay, so this is our one port. Okay, which contains a number of LTI capacitors connected in parallel. C1 is the capacitor of the first guy, C2 is the capacitor of the second guy, and so on. This is Cn. So this is the voltage of the one port, and this is the current of the one port that contains an LTI capacitors. Okay. And V T0, suppose, equals some voltage, which we denote by capital V0. Now, we claim that this can be represented by, or this is equivalent to, this one port, okay, with voltage and current labeled as such, where, as opposed to n devices, now we have just a single LTI capacitor, okay, C equal. And then, for this equivalence to work, we have to answer two questions. We have to figure out two things. First, what's this C equivalent in terms of the givens here, the capacitances? And also, what its initial voltage should be. Okay. Let's answer the second question first, because it's obvious. If this and that, they are to be equivalent, they have to have the same voltage at all times, and therefore, if the initial voltage of this guy is V0, the initial voltage of this new one port must also be the same voltage, V0. Okay, so that's done. The second thing that we have to do is figure out the equivalent capacitance, and let's do that using KCL and the terminal equation. For that purpose, let me label the currents of Rn capacitors, I1, I2, up to In. We don't have to do labeling for the voltages like V1, V2, up to Vn, because clearly they're all connected in parallel. That means they all share the same voltage, and which is V, which is denoted by V. So by KCL, this current, the current of the one port, must equal the sum of those n currents. So let's begin by writing that I of t equals I1 of t plus I2 of t up to In of t. Okay, so that's KCL. And that equals what? Now let's express all these currents in terms of the voltage V using the terminal equation of the capacitor, which we can do easily because it's simply dV dt. So I1 is C1 dV dt, I2 is C2 dV dt, and so on. C2 dV dt, C and dV dt. Okay. And that can be written as C1 plus C2 plus Cn dt, clearly. And the terminal equation for this configuration is I equals C equivalent dV dt. If these two things to be equivalent, it means their terminal equations must be equal, and that means this number here, the sum of individual capacitances, must equal the capacitance of the single capacitor over there, C equivalent. So this must be therefore C equivalent. Hence, C equivalent equals C1 plus C2 plus Cn. Okay. So to establish this equivalence, you have to do two things. First, you have to pick the equivalent capacitance, the capacitance of this guy, as the sum of the individual capacitances here. The second thing is you have to pick the initial voltage of this capacitor to equal the initial voltage here. Okay? Note that we don't speak independently of the initial voltage of each capacitor, initial voltage of C1, initial voltage of C2, because they're connected in parallel, and by KVL, all their initial voltages, or all their voltages for all times, must be equal at all times. Therefore, we only have this thing, this constraint, Vt0 equals V0. Now let's talk about the dual case. That is, what happens when the capacitors are connected in series, or in other words, can we talk about some sort of equivalence when we have n capacitors connected in series? The answer is, not surprisingly, yes. So let's talk about that a little bit. Capacitors in series connection is what we study next. Okay. Now, this is the case that we deal with. We have n LTI capacitors connected in series, and by doing so we obtain a one port whose voltage we denote by V and whose current we denote by I. Okay. Let the capacitance of the first guy be C1, the second guy C2, and so on. Now here they all share the same voltage because they were in parallel, but each could have an arbitrary current. Okay, that's the truth. Here we have a dual case. They're allowed to have arbitrary voltages because KVL puts no constraint on them like it did here. But since they're in series now, they must share the same current. It must be the same current that's passing through all. Okay. So let's label the voltages. This is V1. This is V2, and this is Vn. Okay, and we will now investigate if it's possible to represent those n components, okay, those n capacitors by a single capacitor. Okay. Where the capacitance to be figured out we call C equivalent, or sometimes it's called C effective. Okay. And by definition of equivalence, this one port and this one port are required to have the same voltage current readings at all times, provided that they are connected to the same circuit. Okay. So, here the initial voltage of all the capacitors was something, it was the same V0. This time, each capacitor may have its own independent initial voltage. So let's label them as V1 T0 as V1 0, V2 T0 as V2 0, and so on. Vn T0 as Vn 0. Okay. So these are the initial voltages, and then if this one port and that one port are to be equivalent, initial voltage here appearing across the terminals of that capacitor must be equal to initial voltage here. And initial voltage here by KVL simply equals the sum of all those n initial voltages. Therefore, first constraint, if we are to establish equivalence, is that initial voltage here, V T0, must be V1 T0 up to Vn T0. Okay. And now the next question is how to pick C equivalent. For that, what we're going to do is, let's write V of t as V1 of t plus V2 of t Vn of t. Okay, so by KVL, this voltage that appears across the terminals must equal the sum of individual n voltages. Okay. And then let's remember the terminal equation in its integral form. We have V1 T0 plus 1 over C1 T0 to T I1 tau d tau. But I1, I2, I3 and all the currents are equal, and they equal to I because the capacitors are connected in series. Okay, so we don't have to introduce extra notation I1, I2 and so on. Everything is I. Okay, I tau, d tau. Okay, so that's V1. And do the same thing for V2. V2T is V2, initial V2 T0 plus 1 over C2 times the integral of the current and so on up to the nth voltage. Vn T0 plus 1 over Cn T0 to Ti tau d tau. Okay. Now, to extract C equivalent, all we have to do now is to rearrange the terms. Let's do that. So this equals, let's collect these constants, the initial voltages, as one piece. Okay, so we have V1 0 plus V2 0 plus Vn 0. Okay. And then since it's always the same current that we're integrating, we can express all those n integrals as a single integration. And when you do that, it's multiplied by something, and that something is no other than the sum of 1 over ck's. Okay. T0 to Ti tau d tau. Okay. And now this is no other than initial voltage of this guy here, and this must be 1 over C equivalent, so that we have the same terminal equations on both sides. Okay, it must equal 1 over C equivalent. Hence, we obtain equivalent capacitance situation for this series. connection, and it simply is 1 over C equivalent equals 1 over C1, 1 over C2, 1 over Cn, okay, for the series connection. Okay. Now, we'll talk about how to deal with current and voltage in parallel and series connection of LTI capacitors. Current division. Okay. Now, what we do now is we try to extend the concept of current division that we're familiar with for LTI resistors to the capacitors. Okay. And we're going to do the same thing for voltage division. So this is the situation. Suppose that we have two capacitors connected in parallel, and they are fed by this current source plus minus V C1 C2. Okay, and then let's call the currents I1 and I2. Note that there is a single voltage because everything is parallel, and that voltage we denote by V. Now the question is, how is this current Is of t is divided between these two capacitors? Okay. So by KCL, Is of t equals I1 plus I2, but what portion of Is visits C1 and what portion of it visits C2? That's something that we will figure out now. So the question is, what's I1 of t and what's I2 of t? So it turns out that we don't have to worry about the initial voltages of the capacitors for the current division, because we're going to use the differential equation form of the terminal equation. So let's write I1 of t in terms of the voltage. I1 of t equals C1 dV dt. Okay. Likewise, I2 of t equals C2 dV dt. Okay. And that readily gives us the ratio of I1 to I2. Okay. dV dt equals I1t over C1, and it also equals I2t over C2. Okay. Therefore, I1 over I2 must equal C1 over C2. We have I1 of t over C1 equals I2 of t over C2. Let's call this equation 1. Another equation is coming from KCL. KCL implies that I1 of t plus I2 of t at all times must equal the current supplied by the current source. Let's call this equation 2, and combining equation 1 and equation 2 allows us to express I1 and I2 in terms of Is. Okay. So 1 and 2 yields I1 of t equals C1 plus C2 Is of t, and I2 of t equals C1 plus C2 Is of t. Okay. So it means that larger the capacitance, okay, compared to the other capacitance, the larger portion of the current will be flowing over that device. Okay. Now let's talk briefly also about voltage division, which is a little bit more subtle because we have to also take into consideration the initial voltages. Note that in this in current division we didn't need to use information regarding the voltages of the capacitors or the initial voltages of the capacitors. But for voltage division we have to be more careful. Okay, now here is the circuit that we will analyze. Okay. We have two capacitors in series and it's connected to a voltage source as follows. Okay. And then we have a switch here. That's initially open. Okay, so open means that the capacitors and the voltage source are disconnected or they are uncoupled. Okay. At t equals 0, we let the switch close, we let it shut. Okay. So this is C1, this is C2, the capacitors, and here we have the individual voltages labeled as V1 and V2. And the current passing through them is the same current because they're in series, is labeled I. And here we have voltage of the independent voltage source. Now, V1 initial. By initial we mean the voltage just before the switch is shut. It is something, and that's something we're calling V1 0. Okay, minus 6 volts, plus 18 volts, something. And likewise, the initial voltage for the second capacitor just before the switch is shut is labeled V2 0. Question is, what will the voltages be, okay, if we close the switch at t equals 0? For t positive, okay, t positive means after the switch is shut. Now the reason that we have a switch is because we want to consider the general case. If we didn't have a switch by KVL, this V1 0 and V2 0, they wouldn't be independent because by KVL, this sum and that sum must equal Vs of t or Vs initial. Okay? But we want the initial voltages to be independent and arbitrary. Therefore, we have this switch which is open initially, and since it's open, KVL is not doesn't put any constraints on the initial voltages and Vs of t, and therefore we can pick any initial voltages that we want. Okay? But once the switch is shut, the constraint becomes active. Okay? So this voltage was that voltage must equal the voltage provided by the voltage source. Therefore, those voltages will be this voltage will be shared by the capacitors, and we're going to see what portion of this voltage goes to C1 and what portion goes to C2. For current division, we didn't have to worry about the voltages, but this time the initial voltages do indeed affect the final answer. Okay. Now, since it's the same current that visits both capacitors, we can write V1 of t equals V1 initial, V1 0 minus, plus 1 over C1, 0 minus to T, I1 of tau, d tau. But I1 and I2, they're equal to I. Therefore, we don't need such notation. So everything is I. Okay, so that's V1 of T. Let's do the same thing for V2 of T. V2 initial plus 1 over C2, then the integral of the same current. Okay. So let's put the current on the left-hand side. If you do that, you have 0 minus to Ti tau d tau equals C1 times V1 of T minus the initial voltage. Okay. So that's what we obtained from the first term of the equation, and likewise from the second term of the equation. I tau d tau equals C2 V2 T minus V2 0. Okay. This and that the same, therefore this and that must be the same. So that's a constraint on V1 and V2. The other constraint is coming from KVL. When the switch is shut, when T is larger than 0, clearly V1 plus V2 must equal Vs, and that will be the second constraint. And combine those two constraints, we can express V1 and V2 in terms not only of Vs, but also of their initial voltages. Okay, so let's get rid of the integrals and we can write the following equality. C1 V1 of T minus V1 of 0 must equal C2 V2 of T minus V2 0. Okay, so that's equation 1 or constraint 1. And KVL says that V1 of T plus V2 of T must equal, for T positive, VST. Okay, constraint 2. And the final answer comes by using both of those constraints, and we have V1 of T equals C2 C1 plus C2 Vs of T plus C1 V1 0 minus C2 V2 0 over C1 plus C2, and V2T equals C1 plus C2 Vs of T plus this guy reversed. That is C2 V2 0 minus C1 V1 0 over the same denominator. If we didn't have any initial charge, initial voltage for the capacitors, if both capacitors were empty, then the rule would be quite simple. The voltage is divided inverse proportion to the capacitance values, okay? Where current, so unlike the current, okay, current division. But the rule is not as simple as that when you have some non-zero initial voltages, and you have to have also these corrective terms. Okay, so this is the final answer.